and welcome to the Chemistry Academy. In this video we are going to be looking at National 5 chemistry rates of reactions, specifically the factors that affect the rate of a reaction. If you're looking for help on monitoring the rate of a reaction or how to calculate average rate and interpret rate data, then you can find separate videos on those topics in my National 5 chemistry playlist. So if we get started, in order to get started, if we first discuss how a reaction actually takes place. So in order for a chemical reaction to occur, the reacting particles must successfully collide with each other and then they are converted into products. So this is my little diagram here of particles colliding and turning into the joined product. There are a few factors that affect the rate of a reaction. They are particle size, concentration, temperature, and use of a catalyst. The reason all of these things affect the rate of a reaction is because they end up affecting the number of successful collisions that occur. So the more successful collisions we can create, the faster our reaction will be. If we end up changing something that results in less or fewer successful collisions, then the reaction will slow down. Before we move on to look at these factors more in depth, the particle size essentially affects the surface area, so what area of the particle is exposed. Concentration, you will usually be given a concentration in what's known as moles per litre. Moles per litre is just a unit of measurement to tell us how many particles are in a litre of our solution. So the higher the concentration, the higher the number of moles per litre, means the more particles we have in a specific volume. Temperature, obviously that's how hot or cold the reaction is. Temperature is essentially a way of measuring how much energy the particles have. The higher the temperature, the more energy there is in the reaction system. And then catalyst is something we can use to affect the rate of a reaction by adding it into the reaction. It's not like a reactant because it doesn't end up in the final products. It just helps facilitate the reaction and make it faster. Let's have a look at each of these in a bit more detail now. So we'll get started with particle size. Let's first look at particle size. So like I said, the size of the particle affects the exposed surface area. So this one is the one that probably confuses most people because it is kind of like the opposite to what you would maybe think. So a lot of the time people think bigger is better. So if you have a larger particle, then you're going to have a faster reaction. However, a larger particle size actually results in a smaller surface area. So here I've got a 2 gram block of reactant, and then over here I've split it up in half and made it into 1 gram chunks. So it's the same amount of reactant, but I've just made some of the bits smaller. So as you can see where I've put the green arrows, they are the surfaces that are exposed. So in the smaller particle size, there are more exposed surfaces than in the larger particle. So a smaller particle size results in a larger surface area. That means that you'll have an increased number of successful collisions and then therefore you'll increase the rate. Okay, so the more surface you have exposed, the more area is available for collisions to actually take place, and then therefore you're more likely to have more successful ones and then they'll end up increasing the rate. So for particle size is like opposite to what you would maybe naturally come to in your head first thought. So smaller particles create a faster reaction, larger particles would result in a slower reaction. It's kind of like if you think about the analogy we quite often use is cooking chips. So if you had a big massive chunky chips versus small French fries, the French fries would cook faster than the big chunky chips or the wedges because the French fries have a larger exposed surface area. So there's more surfaces available to the heat to cook them quicker. So for concentration, if you have a higher concentration, it would be like this diagram here, you've got more particles in a given volume. So if you have more particles, you'll have more collisions occurring, which means you're going to have more successful ones just because you've got more happening. So then that's going to increase the rate. Okay, so higher concentration means you'll get an increased number of successful collisions, which will then increase the rate. For a low concentration, it's just the opposite. You've not got very many particles available for collisions, so fewer collisions will take place, fewer successful collisions will take place, and therefore you'll have a lower rate of reaction. Now looking at temperature. So temperature, like I said earlier, is essentially just a measurement of how much energy the particles in a reaction have. So the higher the temperature, the more average moving energy or kinetic energy the particles will have. So they'll be moving a bit faster, they'll have more energy behind them for when they collide. So because at higher temperature the particles will have more energy, there are more successful collisions that occur, which therefore will increase the reaction rate. Now the reason the particles having more energy increases the rate is because every reaction has what's known as an activation energy. So it's like an energy hill that the reacting particles need to overcome in order to turn into products. So if you imagine the reactants here, they have to get enough energy to get to the top of this hill before they can actually be converted into products. Now the activation energy is different for every reaction, so sometimes it can be quite a low energy hill, sometimes it's a really high energy hill, but every reaction has this activation energy hill. So the higher the temperature, the more particles that will have enough energy to overcome that energy hill. So that's why that increases the rate of the reaction, because more particles have enough energy to overcome the activation energy. If the temperature is lower, then that means that on average the particles have less energy, which means we will get fewer successful collisions because not as many particles have enough energy to overcome that activation energy. Therefore, you'll get a lower rate of reaction. So at National 5, you don't need to worry too much about the whole activation energy thing. It's more focused on a higher. However, the reason I'm mentioning it just now is because quite often in National 5, people will get taught that more energy means the particles move faster, which is technically kind of true because they do vibrate more. However, when you come to higher, if you were to write that in your answer, it's not accepted because you need to focus on how much energy or whether they have enough energy to overcome this activation energy. So try to avoid saying that higher temperature means the particles move quicker. Just say that the higher temperature means that the particles have more energy and therefore there will be more successful collisions, so increasing a rate. Okay, when it then comes to using a catalyst, so catalysts are just something you add to your reaction. They're quite often transition metal elements like copper or iron. You'll come across a few of them in Unit 3. And essentially what happens is you add a catalyst into your reaction and the reaction rate will increase. Now the reason this happens is because the catalyst lowers this activation energy hill. So it provides an alternative route. It's kind of like a matchmaker. It takes the reactants, brings them together and makes it easier for them to collide. Because the catalyst doesn't actually act as a reactant, it doesn't get used up. So it's not the same thing as adding more reactant. It's something that doesn't really take part in the reaction. It's just kind of facilitating and bringing the reactants together. So it doesn't get used up, which means that if you add 3 grams of catalyst at the start of your reaction, you'll still have 3 grams left at the end. This is a good thing because it means your catalyst can be reused time and again, so it's quite a good investment if you're running an industrial scale reaction. If you buy a catalyst, then it's not like you're having to buy it every time that you're doing the reaction. The other good thing about using catalyst in industry, which can sometimes come up in Unit 3, so I'd add it in here because it's relevant to rates, is that because it lowers this activation energy, it means you don't need your particles to have as much energy, so the temperature you run your reaction at can be a bit lower. This means that it's safer to run the reaction because higher temperature reactions tend to come with more risk of explosion, and it will mean that then it's actually costs you less money to run your reaction because energy, temperature, heating all costs money. Okay, but the main thing about the catalyst is that adding one will increase the rate of reaction and it does not get used up. Okay, different catalysts are needed for different reactions. So like I mentioned, quite a lot of transition metal elements are used as catalysts, but copper will only be able to catalyze specific reactions. It wouldn't catalyze every single reaction that occurs in the whole world. Okay, so what I'm going to do now is have a look at how these factors affecting the rate can look on a graph, because quite often you're asked to suggest what someone has changed in order to increase the rate or lower the rate. So we'll have a quick discussion on that, and then that'll be it. Okay, so I've drawn this graph of rates results here, where over time we've measured how much, what volume of gas is produced in 3 different reactions. So I've tried to do the lines in different styles. So we've got the solid line for reaction 1, the dashed line for reaction 2, and then the dotted line for reaction 3. So I've given the conditions for reaction 1, so we use magnesium powder, so powder would be a small particle size, 2 moles per litre hydrochloric acid, and 30 degrees Celsius temperature. So if we then look to suggest some conditions for experiment 2, we can see that experiment 2 is a slower reaction because the line doesn't go up as quickly. So we would be looking to suggest conditions for this reaction here. We would be looking to change things that would slow the reaction down. So if we first look at the particle size, so the particle size here is small, so we could make it magnesium lumps instead, or a magnesium strip, so a bigger bit of magnesium. We could lower the concentration, because a lower concentration gives a slower rate of reaction, so we could put that concentration down to 1 mole per litre, 1.5 mole per litre, 0.5 mole per litre, any concentration that's lower than 2. And then if we were to suggest a temperature change, a lower temperature gives a slower rate, so we could pick a temperature that was lower than 30, so say 25 or 20 degrees Celsius. We wouldn't need to pick all of these things, we could just change one of the factors. The rate's not that much slower, so it's probably likely that only one of these things has changed, but those are your options: to change the particle size from powder to lumps, lower the concentration, or lower the temperature. So I'll just keep it as magnesium powder, and I'm just going to lower the concentration to 1 mole per litre instead, and keep the temperature the same. Okay. Then if we look at experiment 3, so experiment 3 is a faster rate because the line is steeper and it goes up quicker. So in this case, when comparing to experiment 1, we'd be looking for things that increase the rate of reaction. So the particle size is already small, so we can't actually change that. That's the best it can be. We could increase the concentration of the acid though, or we could increase the temperature. So you could do either or. So any concentration higher than 2 and any temperature higher than 30. So I'm going to increase the temperature this time as my suggested change. So 2 moles per litre, because we're always comparing to the first experiment for these. And I'll change it to 40 degrees Celsius. So when you get these questions in an exam and you're asked to suggest a factor that could have been changed, it is just a suggestion. There is no one specific right answer. There's quite often a few that you could pick from, like we've kind of just discussed here. So you just need to pick one that you would want to change, or that you could change. Don't overthink it. Just, if the reaction looks like it's slower, pick something, a change that would make the reaction rate slower. If the reaction's quicker, pick something that makes the reaction faster. It's really that straightforward. And if you have a favourite factor, like quite often people find temperature the easiest to understand, then just look at what the temperature was in the first reaction, and if you know it needs to be slower, just reduce that. If you know it needs to be higher, just increase it. Okay, so I hope you found this video on factors affecting rates helpful for your National 5 chemistry. If you did find it helpful, please give it a like, and don't forget to subscribe. Tell all your chemistry pals about the Chemistry Academy channel, and I'll see you again soon.